Assalamu alaikum. This is lab 1 of our microprocessor and embedded system. In this lab we'll be studying doing the basics of our microprocessor. We'll just do an introduction class of this and then we'll move on to the next lab. Okay, in this lab this is the assembly code. This code is basically provided by Sardaram, and all we have to do is to upload this code and check if this is working or not. This is a microprocessor at Mega 328P. We'll be uploading this code on this microprocessor, and then we'll just see what happens. Okay, this is the assembly code. We are basically operating the built-in LED of the microprocessor. So this is the code. So we'll just run the code. And we will upload the hex file here. Let's see if it works or not. Well, we can see that the LED is blinking, so this code works, and now we'll move on to the next code. Similarly, we'll be uploading an .eno code on that is already an example on the Arduino IDE. So we'll be uploading this. The code is pretty simple. It's just LED write data for the built-in LED, which is high, and then a delay of 1 second. And we'll again turn it off for 1 second, and then the cycle continues. Now we'll upload the Eno file. Well, we can see that the LED is turning on and off, blinking, toggling, or whatever. So this code works as well. So we'll now move on to the third code. Well, this is the C code, and just like on the Eno, which I output at port B with a delay of 1 second, and again After that we were turning it off for 1 second. So let's see if it runs. Well, it runs as well. So this concludes our lab 1. We're starting off with lab 2. So in this lab we're going to be doing basically assembly code. This is lab 2 task 1. So we're starting off this. The code starts as the two registers. We're storing the data in these two registers. We're taking output at register 16, then we're adding register 16 and 17 data, and then we're taking output at port C, and then we're clearing the data. So let's run the code. Well, as there is no simulation for task 1, so we're going to move on to task 2. First let's stop the simulation. Now let's open lab 2. So let's wait. So the code is minutes. We're taking register 16 as input, which is on 4D, and register 16 is also as output, which is on port C. Input at receiving data, we're going to receive data from pin C, R16 at pin C. Then we're going to add another register. We're going to add these two registers, register 16 and 17. So we're going to get our output at port B16. Then we're going to clear the data. So let's see. This is the task 2. So wait. So we're comparing this, and you can see the result of the simulation. Now we're moving on to the next one. Now this is our task 3. Two registers, one input, one output. Output at D, port D. Now we're setting 1 bit at pin D0, which will be acting as our output. Now we're storing data in R19. Now after that we're going to make a loop which will decrement R19 and then show output at port D. Then it's going to add R16 and 18. Then it's going to start the loop all over again. Now we're going to this is basically the charging cycle. No. So we're going to move on to the next one. This is the lab 2 task 4. We're going to run this now. There are 3 registers, 2 input, 1 output. Port B and C are declared as input ports and port D as our output port. Now in storing data of R19 in pin B, and then storing R20 in pin C. Then we're going to take complement of, we're going to compare R19 and 20. And then this loop is going to run, and then after that this loop is going to run. So we're going to move to the simulation. Well, this runs. We're basically comparing these. Basically comparing these pins, and then we're showing this output as a result. So this is the output. Now we're going to move on to our task 5. Opening the task 5. This one doesn't have a simulation, so that's just the code. 1 input, 1 output. A register, R16 input, R17 output, storing 0x19 in register 18. Then we're declaring the output pins, output and input pins. Then subtracting R17 and 18. Then incrementing, then decrementing R18, then moving R16 to R18, then storing R0x80 into 18, then comparing R18, then complementing R18, and then loop starting here, jump here, and then this loop starts again. So let's run the code. Well, it works. So This one doesn't have a simulation, so we're going to stop here, and then after that we're going to move on to lab 3. This is lab 3, which is our 0 to 99 counter. So we're starting off with 3 output pins. Port D, C, B and C are all outputs. So this is the data stored, which is basically 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9 in hex. This is our outer loop, which is going to run from 0 to 9, and this is our inner loop. It's going to run from 0 to 9 as well. When this reaches 9, this is going to have one increment in this, so it is going to continue till 99, and with a delay of 400 milliseconds. This also has a delay of 400 milliseconds. Now this will run towards the simulation. This is the simulation for our lab task 1. So we're going to put the hex file. Now we're running it. So when the clock reaches 0, it has an increment on this one, 9 2. So this completes the lab task 1. Now we're going to move to lab task 3. This is our lab 3 task 2, a 5-bit monitor. So there are one input, one output, and if pin C5 is equals to 1, then we're going to display this on port B, else this. So now we'll move to the simulation. This is a simulation, and as you can see, this runs. So we'll be moving on to our task. This is our lab 3 task 3, I think. Yes, task 3. So we're going to check if our pins are input is even or odd, and if it is even, we're going to display this, or else it is this. So we're going to move to this simulation. Now let's run it. Now this is all the even LEDs are on, so we're going to stop this now. Now we're going to move on to our lab 3 task 4. This is our final task of lab 3, in which we have to use a hex pad to turn on the LED. We're going to press any key and then LED is going to be turned on. So this is the code. So there are 3 outputs. These are the character array which we have designated, and there are 2 loops. This is the outer loop for I is equals to 0 for less than 9, and then port D, which will display a character. Then for input, port D, character J, 409, which is J is equals to 9, C is equals to 0, and then we're going to stop. Now we're going towards the simulation. We just have to press any key and the LED should be turning on. And it it turns on every time. So this completes our lab 3. Now we're moving on to lab 4, which is LCD based. So we have to start with that. Now we're going to open this is our lab 4 task 1, in which we only have to use LED and display something on it. So we're going to move towards the task. We're going to just display this. This is our library that we're going to use. It's very complicated, so I'm not going to into detail in this. Yes, we're going to use this library to display all of this. Now we're going, this is the function, these are the functions that are included in this library: display, clear, and these are the command write function, data write function in the library. LCD initial LCD display, this is the function that we're going to use, and this is also the function we're going to use. Now we're going to the Proteus simulation, and we're going to insert the X file and then display. Then our data is being displayed. So hello, hi, and goodbye. So this completes our lab task 4 task 1. Now moving on to lab 4 task 2. This lab 4 task 2, we have to use a hex pad and a 7-segment display to display what we are pressing on the hex keypad. So this is the code. It is similar to the one we used in lab 3. We're basically declaring an array of 1, 2, 3, 4, 5 up to 15. Then there are R1, C1 and int x. These are the 3 variables that we're going to display. Use we're going to use ports D as our display, our output display, and then we're going to use this. Now the first half 0 to 3, 0 to 3, our B0, B1 to B3 are going to be our input, and the other remaining will be our output ports. We're going to use our basic conditions simply if pin XB isn't equal to 0, then break. If there is no output, then 0. Now this is the main code. Port B is equals to 0 EF, comparing the value as pressed keyboard. Now R1 will be 0, so 0 will be displayed. And simply, and again we're going to use this 0xDF. we're going to be giving the input if this x is equals to pin B, and if not this, then R1 is equal to A. Similarly, we're going to do this for all the integers, and now we're going to do this. Lab 4, we'll go task 2. Now we're going to run this. The input is, well, there is some output display, but the output is a little bit off. So this is 1, this is 2, this is 3, and this is 4, 5, 6, 8, 9, 0. This is also 0. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So now we're moving on to lab task 5. And this is our lab 5 task 1, and this is based on timers and counters. In this we will have to display hours, minutes and seconds on an LCD, basically a clock, a digital clock. So this is our basic. We're going to start from here. This is our libraries, and these are our unsigned characters and the integers. These are our minutes and second variables, and this check is for 1 second delay. Now digital read and digital write data. This is going to, initially everything is going to be 0, and then we're going to check if there's anything, and if not, then there's going to be digital write. Now timer integer. These are the registers that we're going to use. This CTC mode operator for timer 1 and no prescaling. We're going to be using a serial interrupt, a global interrupt. Now this is basically for checking to see, for counting. This is for seconds, this is for minutes. If check is equals to 1000 millisecond, then second is going to be 1. Check is equals to 0, then second is going to 1, and so on, incrementation. And 1 minute if second is greater than 59 seconds, then there's going to be 1 minute. And similarly for 1 hour, minutes 59, and then it's going to be an hour. If hour is equals to 24, hour is equals to 0. Now this is the void, the main function. We're going to initialize the LED, and this is basically our interrupts and all the functions being called here. And this is our display OCR 1A. Calculating value for 1 second, started the timer. This is the timer start, and this is going to be our second, minutes and our function being called to be displayed. So now we're going to run it, and let's run the simulation. And it works. So when this second run to 59 greater than 59, then it's going to be 1 minute, and so on. Now we're going to move on to our interrupt display. Now just simply we're going to display all the digits from 1 to 15, from 1 to 3, 1 to 9. Then it's going to start ABCD, and then this is our CTC mode. We're starting with CTC mode. Now these are all our registers. We're going to initialize I1 is equals to 1 and character is equals to I2. Now if we're going to use this while statement TIFR1 register, and we're going, this is basically waiting for timer to roll over. This is the condition for rollover. Now IOTA ITOA function is called, and then we're going to display. This is going to be displayed on the LCD. Now let's run this, and look, it's going to run from 1 to 9, then it's going to start ABCD. Now that's all for lab 5. Now we're moving on to lab 6. This is our lab 6 of SPI, data transmission. Now this is the master microcontroller. This is the code from the master microcontroller. As you can see, all this is basically everything. These are two functions, send data and initialize as master. This is all the data that is being sent or stored as our database. Initialize as master, we're going to use these as our ports for first half as input and the other half as output, port D. Now we're going to apply all the conditions for the display. These are all the conditions. Now these is for sending data, A1. These are all the conditions, and if these conditions are, we're going to send the data, and after 100 millisecond delay we're going to send this next data is going to be, and so on and so on. These are all the registers that are being used for port BF1 and 1 less than S. They are not equal to port B, then SBTRU, and so on. Well, you can see all this from the code. Now we're going to run the simulation of SPI. Oh wait, first we have to do the slave one. This is the data for the slave. This is only has in the master we're going to use the hex keypad here, and it's going to send the data to the slave, which has an LCD connected to it. So when we press any key on the hex pad, the data goes from the master microcontroller to slave microcontroller, and then it displays on our LCD. And this is the data. This is the basic code. You can see the code is pretty simple. Now we're going towards the simulation. We're running a simulation, so let's one is showing 0 plus minus multiplication static 9 8 4 5 6 1 2 3. This is all the data that is being sent into the world. So this completes our lab 6, and all the other processes are all similar, like UART and IC2. They're exactly the same. We're going to attach one master and one slave, and then we're going to send the data over. Now we move on to lab 7. In this lab we're going to be using interrupts and then displaying this lab is basically about interrupts. We're going to use interrupts to display on our LCD by pressing buttons. Now first we can see these both port B and C are declared as output ports. One is for data and one is for control, and port D is input port. Now on port D we're going to use this pull up, and now int I is pull up, which is PD0 and PD1. Now making int 0 and I ground level, these are being declared as ground on 0, and we are enabling these interrupts. Now this is the global interrupt SCI. Now this basically our LCD initializing, data press button. Now ISR vec 0, we are going to be using this button 1 and now button 2. If this is our ISV of int0 vect is pressed, then it's going to display button 1, and if the other is interrupt enabled, then we're going to be displaying in button 2. Now let's go to our simulation. Wait, we just have to change the device. No, the device is alright. So let's move on to this. We're going to import the hex file. Okay, now press button. Now if you press this button, let's wait. on, and now button 1. Now button 2. So this is our lab 7. Now we're going to move on to lab 8. It's simply using interrupts. Now we're going to move on to lab 8. This is basically a temperature sensing lab. We are going to integrate an analog temperature sensor and then display it the temperature on an LCD. So this is basically this. We are going to have to take an analog input and convert it into digital, and then display the digital form on the LCD. These are basically all these are two variables that are being declared. One is the count and the other is an array of 10 numbers. 3 ports are being declared. One port A as input, port B and C as output port. Now we're going to see this. These are all basically the registers: AD mux, multiplexer, and F1 multiplexer, mux 0 and mux 2, channel, and ADC SRA, serial analog to digital converter. So we're enabling this, and then we're going on to the LCD. In the while loop LCD string temp, this is going to be the starting, and then we're going to use ADC ADC register ADSC, while ADSC is equals to this and this, and this is basically the calculation being done. All the calculations being done here, and then we're going to display this calculation on the value of the Celsius. So this is basically all the code. So now we're going towards the Proteus. Well, the code is running, but there is nothing displaying here. So we can say that there is some issue here, but well, it's not displaying, so we'll move on to the next one. Our next lab is lab 9, so we'll be moving on to the next. This is our lab 3. In this lab we have to show the duty cycle, 50% duty cycle of LED, which means that it will go from 0 to 50% of its maximum value, and then again from maximum value to 0. So this is basically our duty cycle. Initially our duty cycle is 0, and then we're going to be making these as our this is our input port, output port, and these are all the registers, and we're making these bits high. we're enabling this register. And this is the duty cycle formula. OCR is equal to duty cycle divided by 100 multiplied by 255, which is maximum value for an 8-bit. This is basically our delay, which is increasing duty cycle. If duty cycle is less than 100, then duty cycle is 0, else this will be following. We are incrementing with 10%. So let's move on to the simulation. Initially 0, then it's moving 10% increment. And the wave size increasing, wavelength. After this is going to start back again from 0. Now let's move on to lab 10. Well, these are all the microprocessor lab. The next we're going to move on to the embedded system, the FPGA, which is going to be done on Quartus. So we're going to close all the Proteus. There's not going to be any physical simulation, just everything is going to be done on Quartus. No Proteus and Atmel will be required for lab 10 to 14. This is lab 10 of Verilog, which is being done on Quartus. Now this file is being compiled right now, so after compilation we'll see the results. Well, this is going to take some time, so we're going to fast forward in the video. Well, the simulation was successful. Now we're going to the output. This is the circuit diagram of. Now we're going towards our wave output. This is the wavefinder. We're going to add the nodes now. Now these are all the nodes. These 3 are our input nodes and these 4 are output nodes. Now we're going to give them time, let's say 100 milliseconds. Let's make it 50. Let's make it 25 milliseconds. Now we're going to run the simulation. The simulation is running and successfully built. Now let's see what the output is. and these are all the outputs from D2H. We can verify them using the truth table. So similarly, all the other labs are going to be done like this. We're going to just copy paste the code that the server farm has provided us, and then we're going to see the results. It's quite simple, and we don't have to do all the labs because all the labs are quite similar to this one. So this concludes all our lab videos and simulations for all the lab from 1 to lab 14. Lab 14 being similar to these, not included. So we are done with the lab.